So there's this question, probably for someone's class. Cyclic neutropenia, a blood disorder in humans characterized by periodic fluctuations in the density of a certain kind of blood cell, neutrophils. All of that was just words, right? We could look at this question and be like, that part doesn't actually matter. I mean, it matters. It's good to have the context, but really, like, I'm not looking at any of this when I read this question. I'm looking at this. The density of neutrophils reaches a high of 2,000 cells per microliter. Is that what the little mu stands for, micro? Actually, you know what? It doesn't really matter. We can copy the symbol and pretend like we know what it is. So the density reaches a high of 2,000 and lows near 0. The period of fluctuations is approximately 3 weeks. Okay, so we've got a high of 2,000 microliters. I think that's micro. Pretty sure. Yeah, it is. Good. Thanks. And then we have a low of 0 approximately, and we have a period of. Oh, that pen is dying. It's too bad. Yeah, for sure. Don't hesitate to ask me to scooch things any which way. Oh. So, yeah. Kevin, well, don't worry about the attendance. I'll figure it out. I shouldn't minimize that though. So, just as a reminder for those on Zoom, the things you write in the chat, everyone can see. Not that it's a huge deal about your attendance, but we'll get it figured out. Oh, that's yesterday. So, for this one, we have a period of. Oh, sorry. Thanks. Period of 3 weeks. And I'm just trying. So the thing is, to me, I probably don't want my period to be 3. Like, I feel like they want me to measure this in days. Not that I've read that yet, but let's go ahead and read it. Period fluctuation. Model the temporal dynamics of neutrophils in days. Yeah. So really, our period, we don't want it to be 3 weeks. We want it to be 21 days. The density is maximal on day 0. Okay, so I know what this graph looks like now from what they've said. I know it's periodic, it's sinusoidal, meaning it's like a sine or a cosine, and it's going to start at a high of 2,000 because they told me it did. And then 21 days later, we're going to be back at that same height. Because that's what a periodic function does over its period. It gets back to where it started after one whole period. And then where should the low be? And the low, I think they said that 0 is the high, right? The density is maximal on day 0. So our density is 2,000 here, and it's also 2,000 21 days later. Thanks. So where should the low be if we know it's like a sine or a cosine function? I know this is really helpful, but the point is, right, we know this is the high, so then it has to do what? It can't go up, it has to go down. And where is it going to hit the bottom? Well, so the bottom value is definitely 0. Right? We're not, so they tell us it's 0, not negative, although a different one could be. But the question I'm asking is, what day are we hitting that 0? 10.5. It's the middle of the highs. So if you've got a sinusoidal function, the lows and the highs each occur like half of the period apart from each other.
Where does the low of 0 microliters come into play?
Well, that's what, so we're about to graph it. The low is right there at day 10.5 in the middle. Thank you. And at a value of y equal to 0. So we know what this function looks like. It looks like a, well, I'm not going to say those words just yet. Thank you. It looks like this. So it looks like we've taken some sinusoidal function and shifted it up by 1,000 and stretched it also by 1,000. So I would say I have something like y, or I could use a function. I could say the density, I'm just gonna say y equal to 1,000 times trig function of, I don't know yet. Have to figure this out, plus 1,000. Because I know that a sine or cosine function goes between -1 and 1. So when the sine or cosine function is -1, 1,000 times -1 plus 1,000 is going to be 0. My low. And when the cosine or sine function is equal to +1, 1,000 times 1 plus 1,000 is going to be my high of 2,000. So I know that this is what I want. I have to kind of figure out what's going on here. And now, really, there are lots of different answers you could actually come up with. You could make it sine if you wanted to. Sine is not what I'm going to pick here, but you could make it work with sine if you did a horizontal shift. So that's more work than we want or need to do. What we should pick here is the one that this actually looks like, which is cosine. Cosine of something that makes it so my period is 21 days. I know the period is going to be 2 pi divided by whatever the coefficient of time is. So usually we say that's the coefficient of time. We often give it a b value. And I want this period to equal 21 days. So if I'm trying to find the coefficient, essentially these can swap places, and 2 pi divided by 21 should be the coefficient that goes there. If you're not sure about this value, and I often am not, like, is that really the right value? Here's what I want you to think about. For a cosine or sine function to go through one full period, we have to go from, how do I say this the right way? To get one full period of a trig function, you want one full what of the circle? We want one full revolution of the circle. If you do one full revolution of the circle, starting here and ending there, you've gone through all the angles. And right, because of the angles, it's the repeating, you're using the same trig function values out. So we're going from 0 radians to how many radians? 360 degrees, or 0 radians to how many radians? 2 pi. So if t goes from 0 to 21, well, 2 pi over 21 times 0 gives me an angle of 0. And 2 pi over 21 times 21 gives me an angle of 2 pi. So we're seeing that, oh yeah, we are getting the full period because we're getting the angles to go all the way from 0 to 2 pi. So we need to get one full cycle. So this would be our answer. Okay, let's talk about a few domain and or range questions. Remember, yeah. Oh, that one looks tricky. Yeah. So let's look at, I'm going to change letters here. Let's look at f of v equal to v plus 11 over 6 plus 3 over v plus 2. That looks unnecessarily complicated. But what I want to find out is, what's the domain? Or really, the question you're really asking yourself when you're asking what's the domain is, what is not in the domain? What's something that's very obviously not in the domain right away? What can v not be? Definitely. -2 is not allowed, for sure. Now, it's actually really worth noting that because a lot of the times people simplify things like this by doing this. We don't really need to do this here, but you might sometime simplify this by multiplying it by v plus 2 over v plus 2. So that the numerator, okay, the numerator is going to be v squared plus 13v plus 22. And the denominator is 6 times v plus 2 plus 3. So it makes it look nicer, right? Now the problem with this, it's a small problem, but it is a problem. The problem with this is that it's less evident that v is not allowed to equal -2. It's still true, but we have to remind ourselves that if we write it this way, if we simplify it, it's like, oh yeah, and v can't be -2. That's not really a concern here because we're not really concerned about simplifying it, but just so you know, right, when you modify a function, if you're asking about the domain, you should always look at the original expression to see what you're really not allowed to have. And then we also have to worry about the larger denominator possibly equaling 0. So now that's probably where I would multiply both sides by v plus 2. So I have 6 times, right? So it is going to amount to this simplified denominator equaling 0. 6 times v plus 2 plus 3 equals 0. I just multiplied everything by v plus 2 on the left and the right. Then you got 6v plus 12 plus 3. So I've got v equal to -15 over 6, which is -5/2. And I guess I really want that to not equal that. So what's in my domain? Everything except those two values. V can't equal -2, v can't equal -5/2. If I was writing this out in the way you're probably expected to write it out, here's -2, here's -5/2. I don't want those, but I do want everything else. So my domain would be everything from -∞ to -5/2, union -5/2 to -2, union -2 to infinity. Yeah. Normally I would lick my finger when I get the number, but I just won't do that. Okay. Looks good. A couple more of these because I think there's 2 of these that look really good. Something I can clarify. We could do this. I'll do it for you guys because I like you. You can do that if you want to see things better. You just have to let me know when we're out of frame because, like, obviously, I'm not always going to know. Cool. Spread, yeah. Oh, yeah. Someone was going to. Let's see. So, I got it. It's curious. Well, we'll see. We'll see, but then this will be in the way. So, yeah. That's cool. We'll take a look at that. Let's look at this next one. Let's look at something like f of t equal to the square root of 7 minus t minus, sorry, t, that's not a 2, that's a t. Yeah, of course you can. Minus the square root of, that's fine, I already wrote the square root of, I don't know, 1 plus t. So here, again, we're just trying to find domain. All right, well, let's see. I've got 2 different competing things here. From this, I know the insides have to be greater than or equal to 0. It's always true for a square root. Same thing is also true over here. All right, well, I can solve both of these inequalities. For this one, I'm just going to add t to both sides. You could also, I always really prefer to do things so that my variable ends up on the side where it has a positive coefficient. You could totally go this way, be like -t greater than or equal to -7, and then multiply it by -1. But I feel like you're doing more work than you need to, right? You could just instead be like, oh yeah, add t to both sides. They're both the same. I just think this is faster. But do whatever you like. Just be careful, right? When you multiply both sides by negative, you have to change the direction of the inequality. Over here, we get t bigger than or equal to -1. And now here's the thing that we have to recognize. Both of these conditions have to be met. It can't be just that t is less than or equal to 7. It can't be just that t is greater than -1. We need both things to be true. So our domain here, written as an inequality, is that t has to be between 7 and -1. Or that t is greater than or equal to 7 and t is less than or equal to sorry, t is greater than or equal to -1, and t is less than or equal to 7. As an interval, it would look like this. And you can justify that to yourself if you want, right? We look back at the original expression. We can see, oh yeah, well, if t is bigger than 7, that's a problem, right? If t is 8, it's fine here. Square root of 1 plus 8 is 3. T can't be 8 here. Square root of 7 minus 8 is an imaginary number. And vice versa. If t was, -2, -2 is fine there. -2 is problematic there. So we can't be outside of this domain. I will mention, I don't remember if I mentioned this before, eventually, mostly in the third quarter of this class, we will deal with imaginary numbers on a pretty regular basis. So we should at some point make sure we develop some comfort with talking about the square root of a negative, negative number. It's not like a huge, well, no, it's a not insignificant portion of this class. So we will be using the quadratic formula, and sometimes those results will give us imaginary roots or solutions, and we will talk about what those mean. That's still a ways away, though. So let's look at, I got two more I want to do. We put another one on here. How about, now we're going to talk about the domain and the range. So let's look at this function, the square root of 49 minus x squared. Domain, same kind of deal as before, in that stuff inside the square root got to be non-negative. If I were solving this, I would choose to factor. I would say 7 minus x times 7 plus x has to be greater than or equal to 0. It is also an option to say 49 is bigger than or equal to x squared, and then taking the square root of both sides, 7 is bigger than or equal to the absolute value of x. Because the square root of x squared is the, oh, sorry about that. Because the square root of x squared is the absolute value of x. But I wouldn't do it that way. I would do it this way and use the number line. Say, okay, well, x is 7 or x is -7. Those are the values that make that expression equal to 0. And then I'm going to pick numbers like 8. 7 minus 8 is positive. Sorry, 7 minus 8 is negative. 7 plus 8 is positive. And then negative times a positive, it's negative. Picking 0, we get a positive times a positive. Picking -8, we get a positive times a negative. Since we want to be greater than or equal to 0, we want this, and we want the endpoints. So our domain here would be -7 to 7. But what about the range? So there's a couple ways of finding the range of a function. One way that's not really an option here is to find the domain of the inverse function. Problem is this function isn't really invertible. So I imagine most of you know how to find the inverse of a function, right? You switch x and y, you solve for y. It's not that you can't do that here, it's that it doesn't really yield the right result. So if you did that here, you'd end up with not the right answer. Because this function really isn't invertible, even though the algebra still kind of mostly works. This one, we should really just think about the graph of it. What kind of shape is this function? Y equal to the square root of 49 minus x squared. I should say it is a well-known shape. Well, so I'm trying to make sure you're on there. If we square both sides, you get this. And then if you add x squared to both sides, you get x squared plus y squared equals 49. And that equation is the equation of a, right. So this equation is the equation of a semicircle, because y can only have positive values in this particular expression. So this is the semicircle centered at the origin of radius 7. And we can definitely see that the range is, well, the y values go as low as 0 and the y values go as high as 7. So the range here is 0 to 7. That is one way of finding the range of the function, is just thinking about the graph. And also really like you could pull out a graphing utility and actually graph it and see what the range is. That is also an option to consider some of the time. Excellent question. So I will point out, looking at the questions that someone sent me about doing in range, it doesn't look like any of them are intended for you to do that, but that doesn't mean we can't do that. So here's the idea. Let me think of a good function. Sure. Yeah, that's sorry. I'm just trying to be like, how complicated do I want to be here? Really? Yeah, sure. Let's go that way. So let's say we have this function, f of x equal to 3 minus 4x over x plus 2x plus 9. And I want to find the range of this function. Well, first off, let's just talk about the domain for a second. What's not in the domain? Negative how much? I think it's not quite -3. If x is -3, we get -6 plus 9 in the bottom, which is okay. Yeah, negative fraction. Or -4.5, right? -9/2, -4.5. Essentially what we're doing, right, is we're just setting the denominator equal to 0 and solving for x. Great, so that's the domain. Here's something I want you all to think about for a second. To find the inverse function, what do we do? What's the first step? Yeah, I heard someone kind of whisper it. We switch the variables. All the y's become x's, all the x's become y's. All right, let me ask you again. When we find the domain, we're finding out what the values are. The x values, or the allowed x values, if you want to say that. And so when we find the domain of this function, we're finding the allowed x values. And if we were going to find the range of this function, we'd be finding all the allowed y values. Okay, but now we're switching x and y, which means after we switch x and y, if we want to find all the allowed y values here, we're really going to be finding all the allowed x values in the inverse function. So it's a really long way of saying the domain, which is just the x values of the inverse function, is the same as the range of the original function, which makes total sense because we're just switching the things. So that's what we're going to do. We're going to find the inverse function and then find its domain. Now, again, I will stress, you can only do this if the function is actually invertible. And the test to see if a function is invertible, the easy test to see if a function is invertible is really to graph it and then ask yourself if it passes the horizontal line test. So a quick example of a function that's not invertible is y equal to x squared. Not invertible because it fails the horizontal line test. And really the idea here is that a function isn't invertible if when you switch x and y, it's no longer a function. Right? If we interchange x and y here, instead of have y equals x squared, we have x equals y squared. This looks like a horizontal parabola. That fails to be a function. It fails the vertical line test. So a function that fails the horizontal line test, its inverse relationship will fail the vertical line test and not be a function. That's very short explanation of why some things are not invertible, because they fail to be one-to-one, which is the horizontal line test. Okay. So we're going to find the inverse here. We've got y equal to 3 minus 4x over 2x plus 9. We're going to switch x and y. So x equals 3 minus 4y over 2y plus 9. And then we're going to solve for y. So I'm going to multiply both sides by 2y plus 9. So I've got x times 2y plus 9 equal to 3 minus 4y. And then I'm going to distribute. Thanks. I'm going to distribute and get 2xy plus 9x equal to 3 minus 4y. I'm trying to solve for y, so I'm going to bring all my y's to the same side. 2xy plus 4y, and all my non-y's to the other same side. Negative 9x plus 3. And the reason we want those y's to that side is so we can factor out a y. So I'm going to have y times 2x plus 4 equal to negative 9x plus 3. And finally, divide by this. So I get y equal to negative 9x plus 3 over 2x plus 4. There's my inverse function. F inverse of x is negative 9x plus 3 over 2x plus 4. And notably, the domain of this function, well, 2x plus 4 can't equal 0, which means we're going to exclude where x is equal to 2. X equal to negative 2. Sorry, I misspoke there. Negative 2. So our domain here is everything from negative infinity to negative 2 union negative 2 to infinity, which means that is the range of the original function. So the range of f of x equal to 3 minus 4x over 2x plus 9 is that same thing. Sorry, not enough room. And if you really wanted, you could check. You can see that negative 2 isn't in the range by setting this equation equal to negative 2 and seeing that there are no solutions. It's actually pretty not terrible to do. You can set this equal to negative 2. Sorry, set the, oops. No, it's right, yeah. Set 3 minus 4x over 2x plus 9 equal to negative 2. Multiply both sides by 2x plus 9. And then distribute. And look what's going to happen. Negative 2 times 2x is negative 4x. Negative 2 times 9 is negative 18. And the negative 4x is canceled. And now we've got problems. Right? That's what's going on there. So negative 2 definitely isn't in the range. There's no way that this function can ever equal negative 2. So that's how you can use the inverse function to find the domain. Sorry, to find the range if you want to. Okay, cool. Brain. All that stuff. Okay, let's go ahead and there's so many things to look at. Let's see if I've got this email for about Trinkova yet. I don't think I do. No. Okay, that's all right.
I think you have the homework question folder.
Say that one more time.
I think you have the homework.
Oh yeah, I was just someone said that they were going to send me the Trinkova thing, and oh yeah, that's all right, no worries. I've got the other thing pulled up, which I think is worthwhile. So let's go ahead and remember where things are. Great, there we are. Oh, I don't need that big. Come on. This computer is perfectly fine, but yeah, that kill. I hate that. That just drives me. I don't want it to be big. Stop trying to be big. I just want you to be small. I do that, but I want the thing. You don't know what I want. You think you know what I want, but you don't know. Okay, fine. We'll just be over here like this. You can stay here and not do the terrible thing you do. All right, so the table below contains the average public school classroom teacher salaries, which looks a little dismal. S For an 11-year period, length equals 0, represent 1990 using graphing utility to find a linear model for the data. Okay, so this is from Guy's class, right? Yeah. So he was definitely, has a video that shows you how to do this using Google Sheets, which is definitely open and accessible to everyone. So I would encourage you to use it. It doesn't mean we can't also do it with Desmos, but let's just do it both ways. So let's grab Sheets. Yeah. Yeah. Give me a new sheet. Oh my God. Am I not logged in? Killing me, Google. Killing me. Okay, I'm logged in. All right. A new sheet. And it'd be really nice if this, I'm really feeling like this is not just going to copy nicely, but let's give it a try. Okay, that worked all right. Surprise, surprise. This might not work so well. We'll see. Ah, okay. Too good to be true. So let's just type in the data. Gosh, should be able to see things. So what do we got here? We've got 1996. I mean, we could be smart about this. Can we be smart about this? I don't know. Is this going to pull over like I wanted to? Oh, I did the dumb thing where you want to do first you have to do 1997. Then I think it'll do what you want. Nope, I'm not smart, clearly.
You have to highlight this.
I was going to say, you probably have to do both of them. Maybe this time. Yeah, there we go. Okay, we can be smart sometimes. And then we want the data down here. So we have 39, get out of my way. 39778. And we have what? 41031, 40327, 40907. Oops, that's 4. And 44029. Great. So first thing I would notice is that, oh, sorry, I realized I'm not sharing. Yeah, no, yep, exactly. I'm sharing the wrong thing. Good call. Let me just share the whole darn screen. There you go. Now you should be able to see it. First thing I want to point out is we want t equals 0 to be 1990. So really, those years are not excellent for me. What I really want is just, did I lose 91? Oh, great. No. So I was gonna say something that's not true. We don't have to delete it all, right? We need another column. So we right click, we can insert a column to the left. And we're 1990, and hopefully, did I just close the thing? Probably. 32777. Wow, come on. What's your problem? Cool. So there we go. There's all our data. But like I said, we really want this to be year 0. And then hopefully, let's see if I can do the smart thing here. Yeah, it worked. Okay. Not that it's really hard to enter like 0 once, but still, we try at the same time. Okay, so then you want to highlight this data. And I'll be perfectly honest, I don't usually use, I've never really done this with Google Sheets. Like I watched the video. So if I screw it up, we'll learn together. I think we want like a chart. I think we want to right click. And thank you. Chart. Yeah, one chart, right? Cool. Working. So there's a chart, but it's probably not the one we want. We'd like a scatter plot. So it's a little better. And we want, so I mean, like, I'm right, really, like, I watched the video. I don't remember where all the things are. So now we want to make a linear regression. And honestly, if I don't remember how, I'd probably Google it. Like, okay, well, linear regression in Google Sheets. Whoops. how do you do linear regression? From the insert. Okay, cool. So it's somewhere. Thank you. Right. I'm like, you guys probably, I'm like, why am I showing you how to do this? You probably know how to do this because probably not everyone. Okay, now what? Thank you.
At the bottom. You put the label, use equation.
Thank you. Interesting. Cool. So there's our linear regression, which means that we have, our equation is, right, so it's not exactly how we want to, like, if I was writing the equation, I would write it as, and I'll show this in a second, y equals 1052x plus 32,652. Right, that's what we're looking for. Or really, I guess I should say, right, if I was using better variables, I'd probably write it as salary is 1052 times time plus 32,652, where time equal to 0 is the year 1990. So, I mean, once you've done it a couple times, it's easy to find the things. But right, you need to know where the things are. You can also do this using Desmos, which is honestly what I am more familiar with doing because I've done it before. And I think we can probably just, yeah. Oh, that's weird though. So this is why it would have been good to have made it as a column. If you make it as a column and actually, yeah, that's. Can we turn rows into columns easily? I have no idea. Probably not. It would be nice, but it seems unlikely. So I'm doing this. Why am I doing this way? Because my brain said do it this way. And yeah, I really want, there should be a good way to make a row a column. I don't think there is though. So I guess we'll just type the data. The reason I want to show you this is because Desmos has some functionality that I think is worthwhile. Okay. Cool. So if we take this over, what? Did I not copy it? I've done this before and it worked out just fine. I don't know what your problem is now. There we go. Okay, finally. So to do a linear regression in Desmos, and again, it's been a little while, I think we just want to do y sub, we want to use the same variable names. So y sub 1 and x sub 1, use an underscore to get the lower, right, to get the sub part. You're going to say y sub 1 equals a x sub 1 plus b. And sometimes I'm like, you, except it doesn't work because what happened to my data? Why are you giving me guff? Well, shoot, I'll have to remind myself how to do this because there's definitely a way to do it this way. And man, so right. Yeah, let's find out. So really you can, like, if you want to do things graphically, look it up, right? It's not like someone has figured out how to do it. So how do you do linear regression in Desmos? Okay. Yeah, we just want the answer. Oh, we need the tilde symbol. That's what I was forgetting. You don't want an equal sign there. You want this little thing there. One symbol. all of them. So that gives you everything. It gives you the R values, it gives you the A, which is, so I'm using A, but you could just as easily use M if you like M, right? It's the same thing. So that's going to give you the coefficients and the y intercept. Now, this does give us slightly more precise values right there, rounding it to the nearest hundredth as opposed to the nearest integer. The same idea. And we can't see the data because it's too large. There's my lovely line that looks like a vertical line because its slope is so gigantic. But there it is. Now, the reason I mention this is because there's also a way to figure out if you've got a graph that is linear on a log-log plot or a semi-log plot using this, which I think is useful. There's probably also a way to do it using Google Sheets. I've just not done it that way. So how much time have we got? Not that much time. Let's look at an example from the textbook. So I used to do this what's what I want to say, a much less efficient way. And so the way I used to do something like this, or if I try and see if something was log-log or log-log linear or semi-log linear, which are really the only kinds of log-log and semi-log things we really deal with. And we really only look at exponential functions, which are linear on a semi-log graph, and power functions, which are linear on a log-log graph. That's kind of it. Exponential is just, some constant raised to the x. Power is just x raised to some power. But let's look at an example. Let me make sure I pick an example that's worthy here. This is straight from the textbook. Let's look at 59 from the textbook. So I'm just going to input the data real quick. Let's turn this off. Can I just make a table? Why don't you ever want to let me make a table?
Sorry, what page? You press the plus.
Say that one more time.
You press the plus.
Ah, thank you.
Oh, no. The one
The
that-
other plus, thank you. Yeah, good. So this is section 1.5, problem 59, page 67. So here are my x values: 2, 4, 6, 8, 10, 12. My y values are not quite so nice. They are 0.08, 0.12, 0.18, 0.26, 0.35. Okay, so let's go take a look at these. And if you look at that, you might just say, well, James, that looks pretty linear. And you wouldn't be wrong. It does look pretty linear. Let's take a look. So y sub 2 tilde not equals, let's just use m x sub 2, whoops, x sub 2 plus b. So what's the measure of fit? What tells us if we've got a good fit or a not good fit? R and R squared. The closer to 1, the better the fit. And that's pretty close, right? I mean, 0.9677 is a pretty close number to 1. Question?
How do you do the sub numbers?
Underscore. So you do X and then hit the underscore, which is shift subtract symbol. It's right next to the plus. No problem. But maybe there's something that's a better fit. So here's what I would have done in the past. When you're doing when you're doing a regular graph, you're just graphing y versus x. When you're doing a semi-log graph, you're graphing the log of y versus x. So what I did before, which was kind of time consuming, was I went back and I did the same. Can I copy this? Maybe, maybe not. Fine. I would love to. So I did it actually in Google Sheets. I made the graph and then I copied it. And then what I did was, I was smarter than this back then, believe it or not. And then I did the log of all those values. So I did log of 0.8 and log of 0.12 And it'd be smart if you could just do log of y2, but I feel like I've tried that before and it didn't actually work. Okay, but now what you can do if you do it this way, which I'm going to show you, is there's a better way to do it. You don't have to do all this. I know we're almost out of time here, but I want you to see this. So hang around for just a moment if you don't mind. So you can totally do it this way. And then if we basically gave us a different color here, we can then do the linear regression for that. Y1 tilde, oops, come on, give me the sub 1 tilde, mx sub 1. Let's see. So what is going, why is that seems, those values seem very bad, right? That looks kind of wrong, I'm not gonna lie. That looks like it's, I feel like those, maybe there's one value in it that's really off. Let's take a look before we commit to this. Yeah, there's something, oh, there's a value missing here. Where's, oh, yeah, it's right up there. Oh, it's, ha ha ha. That's the problem. It's not 0.8, it's 0.08. Okay. That looks much better, right? So there we see a look, an even better R value. So that's telling me that this one, which is the semi-log plot, right? So I'm plotting log of y versus x is a better choice. Okay, now, here's the thing to know. If semi-log is what it's going to end up being, that means the original functional relationship it came from was an exponential relationship. So what you can do, instead of doing all of this work, do the following. You can go, love more room. I'm going to look back at my original data and I think, well, I want to know, since if I want to know if it's semi-log, I want to know if it's a good exponential fit, right? Because it would have been an exponential graph if it's semi-log linear. And we'll talk more about that specific aspect of things on Friday. But for now, I just want to show you, we can do a best fit to an exponential. We're using the x2, y2 data. And instead of making it a line, we're going to make it a exponential function, which is something times a base to the x power. So a times b to the x sub 2. X sub 2, yeah. Okay, so that is taking, turn this off for a second, that original data, instead of fitting a straight line to it, fitting an exponential line, and check this out. The R values are exactly the same, or the R squared value is exactly the same as it should be. So this is literally giving you the same information. And it's showing you, oh, look, this exponential thing is the better fit because it's got the better R value than the linear thing, which I turned off, this thing here. What you don't have to do is what I just did, where I did all the log values there. So we'll talk more about this on Friday. And we'll talk about how we can see that. We will talk about how if your data is linear on semi-log, if it's semi-log linear, we'll see that it's exponential. And if it's log linear, we'll see that it's a power function. And it's not too hard to get there, but we should do the work to see.